the multiple layers of regulation that exist within the clock. And again, that suggests its importance. And work by John Hogginish and others has shown that there's a high degree of redundance amongst the core clock genes. When you knock one down, another one comes up to replace its function. And really, BMAL1 is the only completely non-redundant core clock gene. So again, redundancy built into a system suggests its importance. And finally, this observation by Eric Schadt, where he was looking at biological networks across multiple tissues, and he identified a series of networks that were responsible for integrating tissue-specific networks. And at the heart of this, he noticed the molecular clock. And that is a nice way to think about this anticipatory system, that it integrates function across tissues. And of course, as we age, things fall apart. And that's why a feature of the aging process is the deconsolidation of clock-driven consolidatory networks, such as wakefulness and sleep, for example. So again, you've been through many sophisticated lectures over the last few days, and this cartoon doesn't do them justice, but it's just to remind you that the clock is adjusted to run every 24 hours by what we call zeitgebers, or time givers. And the one that we're very familiar with, obviously, is is light falling on melanopsins in the eye to influence the master clock in the suprachiasmatic nucleus. We know that there are clocks in every tissue, it seems to be, and that there are various zeitgebers along with light, such as food and temperature, which regulate those peripheral clocks, and that they receive instruction from the central clock in the suprachiasmatic nucleus. But we know that, a bit like an orchestra, these peripheral clocks retain the capacity for autonomous function. And indeed, we have shown that they are also capable of influencing the center. So, on the one hand, a bit like a conductor in front of an orchestra, each member of the orchestra has the capacity to play their own tune. But generally speaking, they follow the instruction of the concertmaster, but their own behavior influences the concertmaster's behavior as well. So I think it's a reasonable metaphor. There might be, or across a range of different diseases, and as you would expect, it's much more likely that there's going to be a time of day effect if drug exposure is driven by a relatively short half-life. So, as I said, I'm a lipid guy at heart, and we had done a lot of work for a long time on aspirin and its effects on eicosanoids and the metabolism and first pass metabolism of aspirin and the kinetics of its drug exposure. So I was very interested by reports that suggested that aside from its antithrombotic effect, which you're all familiar with, that in randomized trials of hypertensives, there was some evidence that if you took aspirin in the evening, as opposed to in the morning, that there was a blood pressure lowering effect. Now, these trials were performed particularly by an investigator in Spain, Verma, and what we're looking at here is the impact that favors an evening aspirin effect compared to taking it in the morning. And what you can see with these trials that move to the right of this line, that there certainly is that sort of evidence with actually pretty striking hazard ratios, or odds ratios, I should say, but that they're dominated to an extent by this investigator. Not entirely due to this investigator, but certainly dominated by them, that others have not found this effect. And obviously, all the usual features of trial design come into play. Randomized was this, how blinded was it, how large was it, But with that in mind, we were interested to see if we could recapitulate this effect in mice. And we're used to making observations in mice and seeing if we can recapitulate them in humans. So this was a sort of, if you like, an example of a reverse translation, where with these studies from Guangru Yang, we found that indeed, depending on the time of day that we administered low-dose aspirin to mice, we had indeed an effect on blood pressure. These mice were made hypertensive by giving them salt, and as you can see in CT12, there's no effect. And so this was one of these very rare examples where there was controversy in the clinical literature, and where to some degree finding that we could recapitulate the phenomenon in a model system made us begin to think maybe this is actually a true phenomenon. As I said, this effect came from giving aspirin in the evenings as opposed to in the mornings. And although the studies that I'm showing you here in adults in our hospital in Penn and in Cincinnati by John in the pediatric population are reflective of administration patterns in hospital, we strongly suspect that they reflect the patterns that people carry out into the real world once they're discharged. And what you can see is that with low-dose aspirin, whether you're looking at when it's taken or when it's ordered, it dominantly is something that is taken early in the morning as opposed to in the evening. So if this phenomenon turned out to be true, then it would have major clinical implications that just by changing the time of drug administration, you might be able to improve therapeutic index substantially. Well, as a follow-up to our first study, where we found that the dose of aspirin that we were giving was not complete in terms of suppression of thromboxane formation. We did some dose-finding studies, settled on a different dose, and attempted to recapitulate the study. And what we're looking at here is the hydrolysis product of thromboxane A2, which is the main target of low-dose aspirin and platelets. And you can see that depending on giving the aspirin in the morning or in the evening, we have a greater suppression of thromboxane in the morning. And these obviously are in mice, so everything is switched around. And we have a similar effect on PGP2 in serum. So this would affect the drug efficacy is greater in these mouse studies when aspirin is given in the morning. And corresponding to that, the measure of drug exposure shows that there's greater drug exposure looking at salicylic acid, the morning dosing and the evening dosing. And sure enough, we saw there was a functional correlate of that. We were again able to recapitulate our studies where we showed that in the dark phase there was a significant reduction in systolic blood pressure when aspirin was given in CT0 as opposed to CT12. And interestingly, we also looked at thrombogenesis, and we saw that there was a similar effect in terms of the area under the curve of the fluorescent, the accumulation of fluorescent platelets in a model system in which from time-dependent effect and expanded it to include an effect on thrombosis as well as on blood pressure. And again, in the studies in thrombosis, that second cohort, we saw something similar, time-dependent difference in terms of drug exposure and time-dependent effect in terms of suppression of thromboxane or PGP2 in serum. Now, John Hoganish had done these studies earlier when he was looking at the probably 80% of drug targets for the 100 best-selling drugs in the US, finding that about 80% of them oscillated by time. And amongst them, he saw the primary target of low-dose aspirin, which is COX-1, prostaglandin synthase 1. And he found that this was oscillating in many tissues, including heart and kidney, both of particular relevance to its role, in putative role, in blood pressure regulation. and that this appeared to occur out of phase, potentially under the regulatory control of a microRNA. And indeed, when we did studies in mice deficient of this microRNA, we found that the time-dependent effect on blood pressure that we saw in wild-type controls was abolished. So we're interested in how this might be extrapolated to sort of reinforce the concept that maybe this report from randomized clinical trials by Verma of a time dependence in terms of the hypotensive effect of low-dose aspirin in hypertensive patients may actually be real. And currently we're exploring the mechanism further, particularly looking at temporal influences exerted by the microbiome on this phenomenon. Well, besides drugs, we're interested in sex, and this just shows some work that has been performed particularly by Sean Anderson and Soon Tang in Boulevardry, where we looked at males and females subjected to a misalignment protocol to resemble jet lag. And we confirmed what had been seen by many others, that it appeared that many aspects of the clock were more robust in females compared to males. For example, phase angle of entrainment here, and you can see that the amplitude tends to be larger in power in females compared to in males. And the interesting thing that this observation began to set up was that when we looked at a double plot in terms of the response of the animals behaviorally to this misalignment protocol, that the females tended to be less susceptible to the disturbance of misalignment. They varied in their strategies to try and cope with this, but they seemed to resist a response to misalignment more robustly than did males. And then when we began to look at tissues, we saw something quite similar with respect to transcripts. So here we're looking in blue at BML1 and black in HER2, and in the control experiments in both males and females, you can see them undergoing oscillatory gene expression in liver, in ileum, and in kidney. And this oscillatory expression is lost in misalignment protocol in males, but you can see that it's strikingly retained within the females. So when we looked at the transcriptome in liver and the proteome in liver, we found a very similar pattern with respect to the transcriptome. So you can see here time-dependent oscillation of gene expression in the males, and in the misalignment males, this pattern is lost. And you can see that it's largely retained in the females. We saw a different pattern as far as protein expression is concerned. Again, under control conditions, you can see oscillatory expression of proteins in the liver proteome. The approach we took here was by mass spectrometry, but we know also that we use other platforms like Olink, we see the same thing. And under this misalignment protocol, which is less severe than many in the literature, but we had combined this with having the mice on a high-fat diet, I should have mentioned. We saw loss of protein expression in both, but this is an incomplete study in the sense that we are mindful of the fact that in the work of others, rather than the proteins themselves, the post-translational, the modified proteins are the ones that tend to oscillate particularly dramatically over a diurnal time span. But nonetheless, when we looked at the K pathways that these proteins reflected, we saw a very different contrast in terms of the proteins that were either significantly enriched, such as gluconeogenesis, tyrosine metabolism in the males, compared to the females, fatty acid degradation, PPAR signaling, for example, and the proteins that were significantly downregulated in the males compared to in the females. So they came apart with respect to function. We also looked at the microbiome, and we found that in the males, as opposed to in the females, there was dysbiosis, as reflected by the predicted metagenome in the males compared to in the females. And we also found that in the males, compared to the females, there were bugs upregulated in the gut that were previously associated with the generation of metabolites relevant to diabetogenesis. So again, the possibility that this sexual dimorphism was reflective also of functionally, systemic, functionally important effects in the gut. And here we're just looking at differential metacyclic pathways that were up or down regulated in males compared to the much fewer number of pathways in the females. And again, coming back to diabetes, we were particularly struck looking at super pathways of branch-chain amino acids being upregulated in the males in response to misalignment without changing in the females. And again, this pathway has been particularly implicated in diabetogenesis. So actually, if we look at function in these animals before ovarectomy, which is what's shown on this slide, we had shown that there was a difference between males and females in response to the misalignment, both with respect to insulin tolerance and systolic blood pressure. And here we looked at overectomized mice, and we found that in the males who had been misaligned, once they were overectomized, we rescued the phenotype to some degree. You can see here that in the males, the phenotype with respect to behavior, with respect to blood pressure, with respect to the LDL-HDL ratio is rescued, incompletely, but rescued nonetheless by overectomy. So it looks like female sex hormones contribute in some part to this difference between males and females. And of course the big question is this conserved into the human species? Well, here we looked at the UK Biobank, and we found, unsurprisingly, that many of the features of the clock under ordinary circumstances suggested that it was more robust in females than in males. For example, just like I showed you in the mice, the relative amplitude, the phase, and the mesor fit into this, as does the waking time after sleep onset, favor the females. So we looked at shift workers, and we found that both in males and in female shift workers in the UK Biobank, that the incidence of metabolic syndrome was elevated. This won't come as news to you. There's much in the literature, epidemiological literature, to this effect. But more importantly, we adjusted for the type of shift work that males and females did. And as you know, in the main, they tend to differ. And once adjusted for the type of shift work, we only saw this increase in metabolic syndrome in males compared to in the females. So this work should come out very soon in Science Translational Medicine. But prior to that, along with Katie Hachon, I'd written a review which sort of surveyed the literature with respect to sexual dimorphism in molecular clocks. And one of the questions is, why should there be sexual dimorphism? And we speculated that this might be reflective of the historical asymmetric burden that women play in child rearing, never mind in childbearing, where it's completely asymmetric, and that the robustness of their clocks and the ability of the clocks to resist disruption by circadian misalignment may be reflective of their role in the biological imperative. But obviously in contemporary society, this may have implications both for selection for shift work and for transmeridian travel. So let's move on from drugs and sex to age. And as I mentioned to you earlier, there is evidence of our clocks deconsolidating as we get older, particularly with respect to sleep and wakefulness, where we're familiar with older people having difficulty sleeping at night, dozing during the day. And the question is, how can we interrogate molecular clock function? Again, taking the same approach to parsing contributions to variance. And in this case, we looked at the noise across tissues compared to the signal with respect to transcripts that were dominantly influenced by the time of sampling. And reassuringly, you can see amongst these transcripts were many core clock genes. So with that approach in mind, we then looked at function. And again, taking this approach, we could see that many functional readouts, particularly with respect to activity and blood pressure, were predominantly influenced by time of recording as opposed to the noise and intra-individual variability. So this reassured us as to whether using multi-omic approaches and multiple remote sensing approaches, we could begin to characterize a human chronobiome and look for the influence of age in such studies. And finally, before moving on to what we've done with respect to age, in this earlier study, we could also see multi-omic networks that varied specifically by time of day. And amongst them were functional networks related to phenomena that we knew were influenced by the clock, at least in mice, such as neoplasm and inflammation. So in this pilot study, as I said, we just looked at 6 people. We measured very sparsely. We measured in the morning versus the evening. They're the data that I've shown you. We expanded the cohorts down to a younger cohort and compared them to an older cohort. And we sampled them much more densely. Again, we did this morning versus evening comparison, but we also collected data at 4-hour intervals over another 48-hour period. So by comparison, we had a couple of million data points, if you like, in the pilot study, and we got 75 million and counting in the current data. So first of all, we had selected people by age to segregate so-called younger from older. But the nice thing was that we looked at chronological age using the Horvath epigenetic estimator. We can see there was no leap from the older into the younger with respect to the chronological age as well as the temporal age. Importantly, we found that they each seemed to be like healthy volunteers we might have expected them to be. Pretty similar with respect to emotional valence to the degree that we characterized that. And we saw plenty of functional readouts that were within the normal range, but trended in the direction that we would expect in the old compared to the young. So the old is in orange, the young is in green. You can see that the old tended to have a slightly lower grip strength, a lower response time to intellectual challenge, and lower auditory function in the old. And indeed, when we looked at blood pressure, again, these people were not selected to be hypertensive, although that's always a moving target. But you can see blood pressure tended to trend somewhat older, higher in the old. And if we looked at the dipping ratio, we found that this was less pronounced in the old. So there's less dipping at night in the old compared to the young when comparing to their diurnal variability. From their Orr interval, we can derive estimates of sympathetic and parasympathetic function. Again, as we might expect, these oscillate in both young and old, but there's dominance of sympathetic function in the old and parasympathetic function in the young. So again, when we looked at the transcriptome, methylome, the TMT proteome measured by mass spectrometry, the O-linked proteome, plasma metabolome, we saw very similar things in both the young and the old. We saw these oscillating transcripts or proteins or and metabolites in both data sets. And interestingly, and just illustrated here with the O-link proteins and the differentially expressed genes in the transcript data, we saw a bias in terms of these oscillators in the evening, both in the young and in the old. So, more enrichment in terms of time-dependent differences in the evening than in the morning. As I mentioned to you, there's a lot of epidemiology out there around deconsolidation of sleep and wakefulness as we age. And this interesting study is looking at exactly that, with and without excessive daytime sleepiness, but finding that people who deconsolidate early, who are sleeping more in the daytime and in a more disturbed way at night, who do this early, this is associated with early onset of Parkinson's disease. Now these are all associations as opposed to evidence of a causative relationship, but they're certainly provocative, and there are similar types of data out there, such as this one, with, if you like, their representative experiment shown here, where they're looking at activity in young controls. Here's a 24-hour waveform, and that this tends to be dampened in elderly people, perhaps even more impressively suppressed in people that exhibit Alzheimer's disease as the disease evolves. As I say, this is their representative sample, but there are many papers out there with versions of these types of data, suggesting that as we get older, our clock begins to perform less effectively, and indeed we and others have, including Eric Herzog, who is part of this school, have shown that in mice, if you look at older mice, if you break the clock, you predispose these mice to neurodegenerative disease, particularly gliosis. So we have the central network system, and that is that the consolidation of these oscillating functional networks might contribute to age-related disease expression. And what we're particularly interested in is the emergence of networks with age that may actually be causative of this phenomenon. So again, this is a multi-year effort, and we're scraping the surface of it at the moment. But this just illustrates, using a mixomics approach, if we look at the multi-omic data in these apparently healthy younger versus older individuals, we can clearly segregate the multi-omics data in the young from the multi-omics data in the old. So in the study as we performed it, we were empowered to detect many variations in the omics data as a function of time. In other words, we could see these oscillatory signals. And some variations with respect to age. But what we were underpowered to look at was the interaction of age versus time. And this is just an illustration of what an individual plucked out of here would look like, with the so-called centroid of the multi-omics data here, and the distance from that centroid to various elements of the ohm. Now, what we looked at then was the relationship, as in this circus plot, of elements of these multi-omic proteomics data to each other. Red shows positive correlations, blue shows negative correlations, and many things were related to each other. So we were interested to look under the most stringent circumstances, what were the relationships that we first began to detect. And interestingly, FGF21, which for those of you interested in the aging field, has been around for a long time, this emerged as a hub of relevance in these types of data. And as you can see, FGF21, which goes up with age, is oscillating at in both young and old in blue, young in orange, but highly significantly oscillating as a function of time. And it's connected to a variety of things, but amongst them, just for an example, is ApoL1, which has been particularly associated as a player in terms of inflammation in the kidney, and another player in the inflammatory cascade, HMG B2. And again, you can see these differences that are highly significant, and in some cases, in these cases, are more pronounced in the old than in the young in terms of their oscillatory function. And here we're reminding you we're just looking at amplitude, but this is obviously of interest because one of the things that changes in oscillatory function might be relevant to as we get older is the so-called inflammation that's a feature of aging. And FGF21 also related to functional readouts such as systolic and diastolic pressure that I've described before. So, as I said, we were powered, as shown in this p-histogram, in this case in the O-link proteome. We were powered to detect changes as a function of age, changes as a function of time of day, but rather underpowered to see changes in interaction. So we plan to increase our sample size to look for interactions. But in the meantime, we were very interested to integrate our data, dense phenotyping in relatively small numbers of individuals, with data at scale. And again, we turn to the UK Biobank as far as this is concerned. So in the UK Biobank, the same O-link platform has been applied to look at the proteome in almost 100,000 people. And what we were interested to do was to say, is there any evidence for oscillation of the proteome in the UK Biobank? And in the UK Biobank, each individual has one sample taken, and they collect those samples over a 12-hour period. So if you like, it's a hemicycle. And the question is, does what appears to be oscillating over a 12-hour period actually reflect true oscillation? And the power here, a bit like the reverse translation that I showed you with the mice and hypertension, the power here is to actually integrate the dense deep phenotyping that we have in the Chronobiology study, experimental medicine, if you will, with data at scale. And shown in this big box here, we're looking at proteins that appear to oscillate in the hemicycle of the UK Biobank with those that are true cyclers in the multiple samples that we have in the human chronobiome data. So the human chronobiome, if you like, validates, it's one approach to validating, but validates the true diurnal cycling of this large section of the proteome of the UK Biobank. And indeed, down here in the UK Biobank, you can begin to pick up some cyclers that we don't see in the human chronobiome, and that's almost certainly a power issue. And over here we can see that proteins that we call as non-cyclers are non-cyclers in the UK Biobank. So between these three boxes, it's the overwhelming majority of the proteome in the UK Biobank being validated either as a cycler or as a non-cycler by integration with human chronobiome data. And here, as you can see, we pick up some proteins that don't appear to be cycling in the UK Biobank. But of course, the great attraction of this is that we can now make a connection to outcome, because in the UK Biobank we have the numbers that allow us relate cycling or non-cycling, or biological networks emerging or disappearing with age, to actual functional outcome, both to disease states and to death. And we can also parse the UK data to look at different time bands to see over time what's varying with age. So where we're going is to, if you like, interrogate some of the pathways that are oscillatory connections that I showed you in that circus plot, suggest have functional relevance that might be exploited in age, such as inflammation. We want to increase our sample size to be able to look at interaction in the healthy volunteers over time, so that we can, and in fact the preliminary calculations that we've made with respect to that means that it's quite tractable, so probably going to around 40 per group. We want to look in some diseases where certainly our mouse data or fly data might suggest that the clock plays an important role, some metabolic diseases or some neurodegenerative diseases, and see in homogeneous collections of those people, whether compared to age-matched healthy controls, differences are apparent and detectable in the chronobiome that we can then interrogate in the UK Biobank at scale. And where we're heading as far as this is concerned is the possibility of being able to predict aging trajectories. So in other words, can we look at your chronobiome when you're apparently healthy and say this person is predicted quantitatively to have a much more rapid aging trajectory than this other apparently healthy individual. And the reason to do that is obviously that if we identify therapeutics that might delay the aging process or the emergence of age-related disease, we'll want people to start taking them while they're apparently healthy. And to take any drug, even if it's low-dose aspirin, when you're apparently healthy, requires some quantitative measure to suggest that you're at a particular risk. So if you knew you were at a 10 times greater risk, for example, of looking like you're 30 years older in 10 years' time, as opposed to looking much the same, you're the sort of person that these trials will first be performed on for these age-modulated drugs. So all of this is a bit speculative, and I just refer you to this comment by Isaac Asimov, that it's only afterwards that a new idea seems reasonable, and to begin with, it seems unreasonable. And I think this idea of looking at the clock to determine aging trajectories is probably an apparently unreasonable thought at this stage, but we hope with time to establish that it's reasonable. So I described the work of many people and contributed to this. Some of them, like John Hogganish, are collaborators from the outside, whom I've worked with for many years. Another example is Eugene Melmoth, who's in Calico Laboratories, who has worked on the UK Biobank integration of our data. I've mentioned particularly the contributions of Sean Anderson to the sex aspect of things, Karsten Skarka to the human chronobiome data, and many others who have contributed experimental data to what we've done. And one of the great things of our group is we have integrated into it not just people from very different biological backgrounds in their science, but also people with expertise in computational biology and informatics. And I like Leonard Cohen, and he certainly nicely summarizes my contribution to this work that I've discussed with you today. So with that, I'm concluded, and I can stop sharing these slides.
So very interesting talk.
I think you're muted. I can't hear anything. In fact, I can see you're muted. Ooh, lots of feedback.
So am I audible now?
Yeah. audible, yeah.
Okay, so I have a couple of questions. So first thing is that when we see the dosing time dependency of the drug and their plasma half-life, so definitely the drugs which has a shorter plasma half-life are more influenced by dosing time, but some of the drugs even with 18 to 24 hours plasma half-life are also show dosing time dependency. This would shed light at what could be the possible mechanism or reason for that?
Yeah, well, I mean, an obvious mechanism would be oscillations of target. So, independent of the pharmacokinetics, the target might be oscillating. And actually, aspirin's probably a good example. I didn't show it, but there have been studies of pharmacokinetics in different populations, including pregnant women. And in contrast to what we showed you in the mice, where there's clearly a difference in terms of drug exposure based on the salicylate, in those pregnant women, those pharmacokinetic studies, they didn't see a difference with time. But as I mentioned, John shows that COX-1 is oscillating.
Yeah.
In the kidney, have shown oscillation of COX-1 in multiple tissues. So I think just like it's the basis of the time-dependent instruction in the label of statins, the target is probably important in some cases alone, but in many other cases important as well as time-dependent differences in drug exposure due to kinetics.
Okay, thank you for clarifying it. So another question that your data clearly indicate that there is a substantial difference in the circadian resistance to circadian dysynchrony in male and female, right? So do you suggest then any clinical trials on the clock disruption or dosing time dependency? The data should be collected gender-wise, otherwise we may get something.
Yeah, so you know, we're used to, in this field, we're used to telling our colleagues outside of the clock field, oh, consider time. You know, even today, it's remarkable how many studies don't take account of time or even timestamp the collection of their data. But here's an example where in the clock field, when we first did those studies looking at the oscillation of the transcripts in multiple tissues and saw this clear sexual dimorphism, I assumed this was old news. And then when I went looking, I found that it wasn't old news, but in the vast majority of clockworks in mice, people look at male mice, and in the majority of the minority of studies where they look at both sexes, they mix up the sexes, they don't segregate them. So in fact, in the literature of mouse studies in the clock, the number of studies that actually segregate and then examine differences based on sex are the very small minority. So I suspect what we've done is, you know, the first step in terms of looking at mechanistic distinctions between the sexes, but I think going forward, everything really has to account for the potential differences in sex.
Okay, thank you very much. So the last question. So basically, as we have seen from the whole clock knockout studies in Drosophila or mice, when the whole clock genes is knocked out, the lifespan is reduced or early aging, as well as when the aged, mice or the clock is also disrupted. So basically, the disruption of the clock is definitely a known consequence of aging, as you have shown. So whether this clock could be a cause of, disruption in clock could be a cause of early aging also. Basically both cause and consequence of aging as a clock.
Yeah. Yeah, well, I think if you look at the role of the clock in the microbiome, or the metabolome, and so on, it's usually a bidirectional effect. The clock influences the gut microbiome, the gut microbiome influences the clock, and I think the aging process is a similar bidirectional effect that clearly breaking the clock is an influence in aging in mice, and on the other hand, the features of aging, particularly inflammation and the generation of oxidized lipids and so on, rust up the pieces of the clock so it works less efficiently. It's a little bit more complicated than that. We were obviously familiar with the work of Convenor and others showing that in BMAL knockout mice, they have a lifespan that's roughly a third of normal, and they have many features of aging like atherogenicis and neuroinflammation and so on. But actually, Convenor and Yang, who did the aspirin studies that I mentioned some years ago, compared the effect of the conventional BMAL knockout, where BMAL was absent during development, with deletion of BMAL as an adult in the mice. And what he found was very striking. The effects on core clock genes were exactly the same. Everything was flattened. What he found was that the lifespan was unaltered when you knocked out BMAL in the adult. As far as the phenotypes were concerned, some were conserved, though neurodegeneration is a conserved phenotype. However, others were flipped, like atherosclerosis. And the explanation for this, we believe, was shown by some Japanese workers subsequently, that showed that core clock during development is established very late. So that clock comes up, or MPAS2 comes up, late in development to heterodimerize with BMAL and establish a core clock. Whereas BMAL is around in early development, not functioning in its role of the clock. And we think the discrepancies between the two knockouts reflect these off-target effects of BMAL during development. And in that regard, it's worthwhile remembering that in human neurodegenerative disease, although the data are not entirely compelling, the evidence for premature death in Alzheimer's and Parkinson's is extremely arguable. It's not clear-cut at all, but they die early. Yeah. So this distinction between the presence of neurodegeneration and early death that we see in these mice with adult deletion of BMAL may indeed be reflective of the human condition.
Okay, thank you very much, Garrett. And so all the questions I had, so I have no other questions. Other questions?
Okay.
Thank you. That were all the questions that we had from the audience as well. And it was very nice to listen to the talk. It was very informative. Thank you so much.
Okay. Cheerio.